So, we got anything we need to go over from WebAssign or anything? How's it going okay? Alright. So, just kind of a semi-review day, not necessarily everything we've done, but all the derivative rules. Okay. So, let's see. So, where do we start? I guess we start with the power rule, or well, we could do constant multiple rule. You don't have to use it all that often by itself, but just call it like this. So you can move a constant out front and then deal with it at the end if you want to, if you need to. Power rule is if we have x to some power, we want the derivative, we multiply the coefficient out front by the exponent, and then subtract 1 from the old exponent. And then we've got the sum difference rules where you can split it apart at plus signs and minus signs. We won't write those down. They're kind of natural. So I guess our next two would be the product and quotient rules. So I'm going to write them down the way I remember them. This one we would have f prime g plus f g prime. Quotient rule, so that's product rule. Quotient rule have f g prime minus, no, f prime g, sorry, minus f g prime over g squared. And then we had the chain rule. Now let's see what's the best way to write it down. If we have f of g, it'll be f prime of g times g prime. So we're just rewriting all the rules right now. No big deal. And then let's see what do we do next? We did trig next. Did trig functions next. So got 6 of those. Tangent. So derivative of sine, what's it? Cosine. Derivative of cosine, negative sine. Derivative of tangent. Secant squared, yeah, that one's a little harder to remember. Secant squared. Okay, and then got the cofunctions. So secant, cosecant. Cotangent. So cosecant, if you don't remember them, I might have to look them up. I don't remember these three as well. It is going to be minus, yeah. So yeah, I can. These are minus, and then cotangent, I believe, is minus cosecant squared. It's the co-version of the tangent one. So cosecant is negative cosecant cotangent. And then secant is secant tangent. If you can remember one of them, you can remember the other one because like this one starts with itself, right, and then it's tangent, and then the other one's just the co-version, but you got to remember the minus sign. So cosecant cotangent. I just forget which one does what. Okay. Got those six. And then what else? Logarithms. No, logarithms. So have ln of x, then that's 1 over x. Or you can think about the chain rule version of it. We'll have ln of u, so u is its own function. We have 1 over u prime, or u prime over u. And then got the easy one. E to the x, what's the derivative there? E to the x. And the chain rule version is if we got e to some other function, it's just e to that function times u prime. And then what else? If this is some other function like ln of x plus 1 or ln of x squared or something like that, yeah. Then you would have 1 over whatever it was times the derivative of the inside. So it's really, you really don't have to remember these two if you remember the chain rule. Yeah. It's just sometimes it's nice to have them written down so you can see them. Okay. And then that all. We did the inverse trig. We're not gonna have much of it. Okay. Is that all the rules? I think so. Well, then we did implicit differentiation, but it's the same rules. You just have it's just, you have the chain rule. You have dy dx if you're taking derivative of y in there. Okay. All right, so the thing that's a little bit different after you have all these, after you run the whole list, is that now, if you were to go back and do some of our old homework problems, you would probably use a different method than you had to use when you did it the first time around. Like, especially in the first couple of homeworks where we only had the power rule, maybe there were times when you could have made use of the product rule or the chain rule or something like that and made life easier. So we're just gonna run, let's see, I've got 13 problems I think up here, so we'll just find some mixed derivatives. Okay, so there's no particular rule we need to be looking for on these. We just need to figure out what rule to use. Okay, that's kind of a challenge in itself. And there's more than one way to find some of these derivatives. You can make use of different rules. So let's look at this one. We'll start with a pretty simple one and work our way up. Okay. So if we want to find y prime, or dy dx, or however you want to write it down, what do we need on this one? We don't have to have anything too fancy, but what rule can we use? Power rules. All we need power, and then the sum and the sum and difference rules. But top of our list, we just need power rule. So somebody tell me what the derivative is going to be. Yeah, 9x squared minus 2x. And then what happens to the 8? It goes to 0 because it's constant. Okay? It goes to 0 because it's constant. So if you can do that one, that's a good starting place. Okay. Questions on that one? All right. Do those seem easy now? Well, see, that's the some of you, if you've had calculus before, they were easy already, but now that you've done some harder stuff, that makes it seem easy. Easier, anyway. Let's see. Here we want to find h prime. So what are you seeing there? If we're looking at the original function, something stands out to me that I know I'm going to have to do. You see, before I can even take the derivative. Yeah, the eighth root, yeah. So this thing I would rewrite it as t, and so if we change eighth root to exponent, it's 1/8. Yeah, 1/8. And then for that first part, we use the power rule. It's a little messier because we've got a fraction involved. We multiply the 1/8 up front and subtract 1. We do have to get a common denominator, so get minus 7/8. And what about the second term? Yeah. So you can think about it using the constant multiple rule. Okay, we're just going to have minus 8 and then multiply it times whatever the derivative of e to the t is. And the derivative of e to the t, it's just e to the t. And it's itself. There we go. Questions on that one? Think we need to back through? Good so far? Okay. Let's see. we're going to find y prime. Looking at this one, similar situation to last time. It's a little bit different. Yeah, rewrite the cube root, yeah. And if you need to do it in 2 steps, you can. So if we just change it to a fractional exponent, it's x to the 1/3. Yeah. Technically, if we really wanted to, I don't know why you would, but if you really wanted to, you could do it written like this with a quotient rule. Have a constant on top and x to the 1/3 on bottom and do quotient rule. That's not the easiest way to do it, at least not the quickest way. So we could rewrite that one more step. So that'll be not equal plus. That'll be 4x to the what? Negative 1/3. Yeah, move it up to the top. If we do that bit of algebra, then we can not have to worry about quotient rule. We can just use power rule. So the first term's not all that enlightening after the last one. It's just 7e to the x. Then when we do power rule, we have negative 1/3 times 4. So we'll get negative 4/3 is our coefficient. And when we subtract 1 from the exponent, it's negative 4/3. And for our purposes, that's fine. We can leave it like that. We don't have to worry about doing any fancy simplifying. Questions on that one? Okay. Here's another one where we have some options. So I see at least 2 good options on this one. What's standing out to you? What do you think? We could do the product rule. That's a good choice. Or we could FOIL and then use the power rule. Yeah. I think product rules are worth it on this one, maybe. If you wanted to FOIL and do the power rule only, that would be okay. Unless, unless we had instructions that specifically told us to use product rule or something. So there we would take the derivative of the first term. There we get 14x times the second term plus our first term times the derivative of the second term. So there we got 1 minus 2x. And that'll probably simplify a little, but we won't worry about it today. Oh, that's f prime too, sorry. I think that's the derivative part. I don't know. If I do, I'll specify. I'll either say simplify as much as possible, or I won't say that, and then you can leave it. I won't make you do any real involved simplification. So my opinion on that is it's not an algebra class, so I'm not really interested in testing you on a whole bunch of algebra. Just the bare minimum algebra you need to be able to do the calculus. So. That's like you're taking a literature class and then they bust you on misspelling some word in your essay answer or something. Okay. All right. Not this one. Have options on this one. Could do quotient rule. Not too bad. You want to do a quotient rule? We'll do a quotient rule. And then I'll tell you my other thought. Because remember, I am personally, I don't want to transfer it to you. Personally, I'm quotient rule adverse. So doing quotient rule, derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. That's our derivative. That one probably simplifies way down because we've got a 7e to the x in common in the top. We can factor out, cancel that with a 1 to the e to the x's in the bottom, but that's the derivative part. Right. So that's not too bad. That one I would probably go ahead and do quotient rule on maybe. Other option? You may see another option? Yeah. Okay. Do that. Do product rule instead. I might as well try. Let's see. See which one's better. So y prime product rule there. So the way I would think about this is I would group 7x together and then do 7x times e to the negative x. Probably quotient rule is nicer on this one because we have chain rule with the e to the negative x. So we'd have derivative of the first one times the second one plus first one times the derivative of the second one, which is e to the negative x times negative 1. How does that play out there? Oh, okay. No. I was trying to figure out how we were going to get making these match up, how we would end up with an e to the x in the bottom. One of these e to the x's will cancel with the ones in the top, and we'll have one e to the x in the bottom. But these are really in the bottom because they're e to the negative x. So it's probably either way. Either way. I'm crooked. Oh, that's real bad. Pen's acting up a little. Thoughts? What do you think? Basically the same as the last problem. Yeah. Quotient rule is probably the best choice here. Might not be bad moving the denominator up to the top. You can really, as long as the top's not too complicated, that's a pretty viable option. Is moving the bottom up. You could have x times x squared minus 7 all to the negative 1 power if you really wanted to avoid quotient rule. Okay, so derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And that would simplify some. So that actually, so I'm happy with that, but that actually is a pretty nice problem because what do we, that would be x squared minus 7 minus 2x squared. Oh, it's not as nice as I thought it was. Okay. Yeah, so I was thinking that we were going to get positive x squared and get canceled. That's fine. Pull that out. So. Product rule. So we do product rule. Do the derivative of the first one times the second one plus the first one times the derivative of the second one, which is cosine x. Derivative. They're not all nightmare problems. There are some nightmare problems, but they're not all that bad. This one. What do you think? Product, yeah. And I would group it, personally, I would group it like that. Since it's 7 times e to the x times cosine x, you have some flexibility in how you group it. You could group it e to the x and then 7 cosine x, or you could just pull out the 7 as a constant multiple and deal with it that way. So we do product rule. It's the derivative of the first one times the second one plus the first one times the derivative of the second one, which is negative sine x. The only thing to me about having those e to the x terms in there is makes it easier to get lost. Like, is this where I took the derivative, or is this the original function? Which one did I write down there? So if that's fine for that, we could also write it 7 e to the x cosine x minus 7 e to the x sine x. Maybe a little more standard. Question on that one? Ain't in there? Go ahead.
If you have like negative e to the x, then you always multiply by -1 after.
If it's e to the negative x, yeah, because there e to the negative x, that's like e to the u, because it's not just an x anymore. So that derivative is e to the u times u prime. So we end up with, what's the derivative here? E to the negative x, right? Let's just copy itself down, and then times the derivative of negative x, which is negative 1. Really, we're always doing that. If we have e to the x, and we take the derivative, we're really using the chain rule just behind the scenes, because that's e to the x times the derivative of x, which is 1. So yeah, you can think about it with the chain rule just in general, is that we're always using the chain rule. And whether we realize it or not, it's just sometimes that extra derivative gets just a 1. It's just simpler to write it not thinking about the chain rule in those cases. I've only got 4 more. And we're finding dy dx. Okay. What's going on with this one? We've got chain rule, we need to rewrite it. So that we could rewrite it as 1 plus 7x to the 1/3 power. And then that makes chain rule a little more obvious, because we've got this 1/3 power on the outside, and on the inside we've got 1 plus 7x. You see how that's chain rule situation? Okay. So then when we take the derivative, we're going to multiply the 1/3 up front. Just copy down the inside function part. And then we'll subtract 1 from the exponent, so we get negative 2/3. That's like taking the derivative of the outside function. Okay. But then we also need to multiply by the derivative of the inside piece, this piece. So the derivative there, where we're going to get 7. And then chain rule usually lends itself to having some pretty easy simplification you can do. So 7 times 1/3, that would be 7/3. And we'll just leave it negative 2/3. Okay. Actually, I have 4 more now, sorry. Let's see, what about this one? Similar situation. Now we have an inside function and an outside function. Okay. So we need to use chain rule. So we can multiply the 4 out front, leave the inside alone. Subtract 1 from the exponent. And then find the derivative of the inside portion. This one's not quite as simple as the last one. 6 times 7, what's that one? 42. That was always a hard one for me to remember. And then subtract 1. And then 3 times 4 is 12. Track 1. There's our derivative on that one. Is it the messier ones? What do you mean? Okay, so we got f of theta is cosine of theta squared. Yep. Yeah, so product rule we use when we have a product. I know that's when we have like two functions that are just multiplied together, and that's all. Chain rule is more of a situation where we have one function inside of another function. Like here we've got the 1 plus 7x inside of the cube root. So we have to do the outside part and then the inside part on it. There is some overlap where you could use either one. That makes it like if we had 1 plus 7x squared, then either you could write it as 1 plus 7x times 1 plus 7x, do product rule, or you could do the chain rule. And so it does make that a little bit confusing there. But yeah, so f times g, product rule, f of g, chain rule. That one technically, we could write out 4 times, so 7x to the 6 plus 4x cubed 4 times, and we could do a product rule where we had 4 terms, and it's just unnecessary. It's quicker to do it with chain rule. This one though, we don't really have a way to use product rule if we wanted to. And so we've got cosine of theta squared. So the outside portion of this, again, if you have trouble thinking about which one's inside, which one's outside, some of the types of functions we deal with are a little tricky. Think about order of operations. Like if you were trying to plug in a number, what would you have to do first? What would you do after that? So here, the first thing we would do if we were plugging in like pi for theta is we would have to square it, and then we would take the cosine of our answer. So we'll start taking derivatives from the outer part. Okay. So derivative of cosine, negative sine, and we'll leave the inside alone. So we'll have negative sine of theta squared times, take the derivative of theta squared, be 2 theta. 2 theta. And that's it on that one. So if we wanted to rewrite it, we could say negative 2 theta sine of theta squared.
What is just theta? Like if it was just theta, not theta.
Then, yeah, so if it was just theta, so like if we had cosine of theta, then you treat it just like an x, so it'd just be negative sine theta. It'd be just like if it was cosine of x, it's just negative sine of x. Does that make sense?
But on that one, you wouldn't do the chain rule.
Oh, for the theta part, for 2 theta, I see what you're saying. Yeah, no, it's okay, because this is just like this is the derivative of this part. It's not that this part's inside of anything. Yeah, I see what you're saying. Definitely see what you're saying. Yeah, so that's part of a little bit of trickiness to chain rule. When can you stop? Right? When can you stop doing chains?
So if the square was outside of the theta, would that be
I want to do that problem too. I don't have it written down over here, but so let's switch it. If it was like cosine squared of theta. Yeah, because that one's confusing because of the crappy notation, in my opinion. Okay. So to do chain rule, when you've got a trig function raised to a power, to me, it's really helpful to rewrite it and write it as what it means, not what the notation says. So this means cosine of theta squared. I've always struggled trying to think my way through chain rule when it's written like this. Because it's confusing thinking about what's inside, what's outside. Okay. So for that one, not that bad if you remember to rewrite it. So then we would multiply the 2 out front and have cosine of theta. Subtract 1 from the exponent, we'll get a 1. And then times the derivative of cosine theta, which is negative sine theta. And if we wanted to rewrite, we could call it negative 2 cosine theta sine theta. Yep.
Why would that not just be power?
Because this part is a function itself. All right. So we've got an outer function that's a square, and then our inner function is cosine.
So the first one, the cosine square, makes me think they're like separate.
Yes. Yeah. This, I hate this notation because it's confusing. It's convenient. I get why they do it because it's easier to write that down when you have a bunch of different things going on than it is this. But this is way more informative for what's actually happening to me. So in this case, like to find the cosine squared of theta, you can think your way through an order of operations, right? The first thing we would have to do is we would have to find cosine of theta and then square our answer. So that means we're doing this. That's always been kind of a troublemaker. Other questions on that one with the trig functions? And really, that's not too bad. When it's real confusing, like is like if we've got this, then what in the heck's on the inside and what in the heck's on the outside? That's it's worse but if we do it this way, it's easier to see. So then the only thing that would happen would let me just get rid of it. I'm not saying that. I'm just saying this is worse. I'm just saying this is worse. So then, oh no, because you got to live with it. I have to live with it. So you just got to know that it means. Yeah, that's a good thought. Good thought. Yeah. So then we have 2 cosine theta cubed times negative sine of theta cubed times 3 theta.
Would it not be squared? The 3 theta.
Yeah, 3 theta squared. You're right. Thank you. I was like, why are y'all trying to square those trig functions? Yeah, that's right. Okay, and then if you think your way through the order of operations, right? If we were trying to plug in some number, first we would have to cube it. Then we would take the cosine of our answer, and then we would take that answer and square it. Okay, so think your way through trying to actually evaluate the function, it can help a lot. That's getting into pretty nasty territory though. let's look at this one. Oh no, I mean, I was like, oh, I'm gonna leave this other term off because that's nicer, but it's really not. I remember why I put that in there now. Okay. Can do product rule. Okay, can do product rule. So the thing is, we'll do product rule for that first term, and then we'll have minus whatever this derivative is after that. We just can't forget this piece if we do it that way. So if we do it product rule, yes. Yeah, we got a chain rule inside the product rule, because inside the natural log is 6x, not just x. So derivative of the first term, so I'm grouping them. I'm just looking at this piece, and I'm grouping it 7x times ln of 6x. Okay. So then derivative of the first one is 7 times the second one. So on that part, we avoid anything that's too messy. Plus the first one, 7x times, okay, so here, when we take natural log of 6x, we've got two things going on. We got just that we're taking the derivative of a natural log, and then we've got chain rule because we've got 6x in there. But chain rule with natural log is not too bad. Okay? So the derivative of natural log is just 1 over whatever's inside there. But then since we have chain rule, it's times the derivative of what was inside, so 6. And we'll simplify that in a second. And then now we can look at this part, because it's just kind of a tag along. So the derivative of negative 7x is just minus 7. Yeah, now we can simplify a little. It's not too terrible. Uh, 7x times 1 over x minus 7. So 7x times 1 over x, which is 7. Those go away. And we just end up with 7 ln of 6x. Which, don't think about it too much, because if you think about it, that's kind of frustrating. Here, so here we would get 7x over x. X over x cancels, leaves us just 7. Back up a step, yeah. How'd I get this part? Yeah, so inside the logarithm, we had 6x. Yeah. Yeah, 6 over 6x. Is that better? It is. Yeah, 6 over 6x is it. Yeah. Yeah. Some people like to think about it like this better. Some people like to think about 6 over 6x better. So then the 6's and the x is canceled. Get the 7. Okay. But yeah, that is, if you stop thinking about that, it's kind of frustrating, because it's like, why didn't we just stop? And it's just because this doesn't always play out that way. Okay. One more. if we leave it written, you can do it with it written like this. But if we leave it written like that, it's confusing even to talk about what all rules we got to use. Because we have to do the chain rule inside of a product rule inside of a chain rule for a logarithm. We can work our way through it, but then let's talk about an option. So it's going to be 1 over x e to the negative 6x times the derivative of the bottom, which is a pain a little bit, because we got product rule with the chain rule involved. So we got derivative of the first one times the second one plus first one times the derivative of the second one, which uses chain rule. That. I don't know. It just depends on the problem. I won't make you have to do anything real nasty. Try not to. Okay? That's not the way I would do that one, though, if it was me. Well, if you do that, you have to move the whole e with it. You'd have to move e to the 6x. And then we just end up with quotient rule, so that's making it a little bit worse. I'm thinking something else. What else can we do? What else do we know? Forget calculus for a second. Okay. If we want to rewrite that thing, go back to 112. I forget calculus. So. Yeah, you could do it with quotient rule, but yeah, I think it would do. We can, if we have a product inside of a logarithm, what can we do with it? What's it turn into?
Yeah.
Look there, we got ln of e. What happens with ln of e? Yeah. So all this mess that we've got down there should be, we take the derivative in ln of x minus 6x form. It's that. It probably is, if we worked on it for a while. Because we've got, let's see, these cancel with that. So it'll be 1 over x times 1 plus negative 6x. So if we simplified this, we would get here. But to me, it's easier using that one logarithm rule and then, or 2 logarithm rules, right? We split it into some. ln, so if you want to think about it, you can move the negative 6x out front. ln of e is 1. So you end up with negative 6x. And then, ta-da, much smoother. Any questions on any of them? Yeah. Okay. So saying that, okay, if you get to the test and you're getting stuff that looks like this, okay, that might be right, okay, and it is right, it's correct, but don't just think Mr. Stanley's being a butt, okay. Think about maybe there's something else I can do that makes it, maybe it's not that mean. Okay. No, that's a good thought. No, I haven't thought that far ahead yet, though. Okay. All right, so Friday's web sign day. Okay. Monday will be your review. I will try and I will get the practice test posted tomorrow, so you go ahead and have it. Okay, and then, yeah, probably. Yep. And then next Wednesday's the test. Okay. I could, yeah, I might do that. Never know.